Okay, hello once again. We are now on Laplace transformation of a function. Laplace transformation is an alternative way in finding the solution of a differential equation. In this presentation, so we should be able to solve the Laplace transform of the given function. So by first using the definition of the Laplace transform, and then second would be the Laplace transform of common function, so using some algebraic manipulations, and then we have some basic properties so that we could use in finding the Laplace transform of a given equation, and that is through shifting theorem as well as the multiplication by t raised to n. And those are the things that we will be doing so for this presentation. But let us start first with Laplace transformation. As I have mentioned, so Laplace transformation is an alternative way in finding the solution of a differential equation. So when I say differential equation, Laplace transforms function is to transform a given differential equation into an algebraic equation. Okay, so an ordinary differential equation, so once transformed using Laplace transformation, so it will be converted into an algebraic equation, so which could be easier to manipulate, okay, so which could be easier to solve. And then afterwards, so we're just going to transform it back into the differential equation, so for us to determine the solution of the given ordinary differential equation. So that is the idea behind the Laplace transformation. It's just a transformation of a differential equation into an algebraic equation so that we could use algebraic manipulation or the principles of Laplace transformation, so for us to get the solution of the given ordinary differential equation. So to start with, so let's have, by the way, Laplace transformation is used in different applications. So usually, Laplace transformation is common in stability. Okay, so that is used in control systems. Okay, so for in the field of engineering, so it could be used in various fields, so depending on what would be the engineering field. The control system, so where it is mostly applicable or it has a vast application, would be in the field of electrical and electronics engineering. Since we are dealing with electrical systems or electronic systems, so its system so could be transformed into its equivalent differential equation, and then from there, so if we want to control the stability of the system, so using feedback systems, so we can use the principle of Laplace transformation. So in the field of civil engineering, so we could use it as well, although that is not common, but there are some researches, okay, so involving the application of Laplace transforms in structural analysis. So since structural buildings tend to move, okay, so if we want to determine the stability of those structures given those external forces, so such as wind loading or such as earthquake, so we could look into the application of Laplace transformation, because Laplace transformation is usually related in maintaining the stability of a certain system. So whether that would be an electrical, an electronics, or it could be a mechanical system, or as far as even to a structural system. So basically those are the application of Laplace transformation. But on our case here, so since we are dealing with differential equation, so the main idea on the Laplace transform is just to transform the given differential equation into an algebraic equation. So as we could have an alternative method in solving the given differential equation. So let's proceed with the definition of Laplace transformation. So the Laplace transformation is a method that reconstructs a function of a real variable t to a function of a complex variable s. So usually if we are given a function in the t domain or a function of t, so we could transform it into the s domain or the frequency domain by using the Laplace transformation. But in Laplace transformation, for us to transform it into its equivalent algebraic equation, so it must converge. Okay, so it must converge. So that means there should be a defined value. Okay, so once we integrate the given function, so from 0 to infinity, so we should be able to get a defined value, so would that would make the given equation converge. So otherwise, so there are some part, okay, so where it diverges. So that is why the definition of the Laplace transform is confined. Okay, so to certain values. Okay, so where it converges. So technically speaking, so the Laplace transformation symbol, so as we can see here, so it's just an L, okay, and then the Laplace transformation of a function in t, so is equal to the integral of the e raised to negative st. So this is what we are referring as the kernel of the transform, so which is the e raised to negative st. And then the function that we are trying to find its Laplace transformation, so that would be the f of t. And once we use that, so we're just going to integrate it and then evaluate it from 0 to infinity. So that would give us the, once evaluated, so will give us the Laplace transform of the given function. So let's have an example for that. Let me insert a page here so that I could give an examples on how to use the definition of the Laplace transform. Actually, the most common thing there, so the Laplace transform of f of t, so that would be equal to the integral of e raised to negative st, and then f of t dt. That would be evaluated from 0 to positive infinity. So let's say we are to find the Laplace transform of e raised to 80. So the Laplace transform of an exponential function, wherein e raised to 80, a would be any constant, so in t function. So to find the Laplace transform of e raised to 80, so that would just be 0 to infinity, then e raised to negative st. So our f of t is e raised to 80 dt. And then we're just going to evaluate it, or we're going to multiply it. So since both are exponential functions, so we could add the exponents. So that would give us, and then t is common to both. So that would be a minus s, then multiplied it with t dt. And the Laplace transform of the given function, we could integrate the exponential function. So we have the numerical coefficient of t to be a minus a, or to be a minus s. So therefore our neutralizing factor should be a minus s as well. So that would give us 1 over, so a minus s, and then that would be e raised to a minus s raised to t. Then we're going to evaluate it from 0 to positive infinity. So by the way, for Laplace transformation, so f of t, so the t domain, so uses a small f. But if we already if we are already finding the Laplace transform, so in the s domain, so that would become f of s. So we're using capital F for the Laplace transform. The original function is on lowercase f, and then the Laplace transformation is on the uppercase f. So this one would just be f of s. And from here, so 1 over a minus s is considered to be constant. So therefore, our f of s then, so would be equal to 1 over a minus s. Then we're just going to substitute. So e raised to a minus s, a minus s, and then that would be infinity. Then minus e raised to a minus s multiplied it with 0. So in Laplace transformation, there are two things that we could assume here. So that is when s is greater than a, and when s is less than or equal to a. As you can see here, so when s is greater than a, okay, so when s is greater than a, so we would get a negative value. Okay, then if s is greater than a, so we will have a negative value for this particular exponential function, and then evaluating that one, e raised to a negative infinity, so that would make it equal to 0, and that's defining. Okay, so defining or thus making the function converge. Okay. However, if s is less than or equal to a, okay, so we will be getting an undefined value, so thus diverging. Okay, so it diverges the function. So that is why we are going to evaluate this one in such a way that it will converge. Okay, so it will converge. So in this case, so that is when s is greater than a. So our evaluation here is, our assumption is s is greater than a, because if s is less than or equal to a, it diverges. Okay, we will not be able to find a solution for that. So in here, so we could evaluate that e raised to negative infinity. Okay, so e raised to negative infinity, so that would be 0. And then a constant multiplied with a 0 would be 0. So e raised to 0 is equivalent to 1. So as you can see here, so this would become a negative 1 all over a minus s. And then if we want to make that positive, so f of s, so we could factor out negative on the denominator. So to make it positive, so that would become 1 over s minus a. So actually, the Laplace transform of the exponential function, so would just be 1 over s minus a. So that is on how, this is the simplest. Okay, so this is the simplest. Actually, we could try even another one. So let's say I would have, let's say it's just a constant k. Let's say f of t is just k. So what would be the Laplace transform of k? The Laplace transform of k then, so would be, so k is constant. So that is the integral from 0 to infinity. I'll start with k as our f of t, and then e raised to negative st dt. And this is very direct. So that would give us k all over our neutralizing factor is 1 over negative s. So negative k all over s. And then, so we will just have the e raised to negative st. That is from 0 to infinity. So negative k all over s then. So we'll have e raised to negative s times infinity and minus e raised to negative s times 0. So similar with what we did before. So e raised to negative infinity is 0. So this is 1. So negative and negative. So in short, the Laplace transform. Okay, so the Laplace transform of any constant, so would just be equal to k all over s. Okay, so that's the constant divided with the s. So that would be our Laplace transform of the constant. So that is why in Laplace transformation, instead of dealing with this very long method of finding the integral of the product between the kernel function and the function itself, there is actually a table. Okay, so there's actually a table that was developed already. Okay, so there is actually a table that was developed already in finding the Laplace transform of a common functions. So these are the common functions that we are dealing with in terms of algebraic functions. So this is what we derived before. So the Laplace transform of a constant is just c all over s. And then the other one, the exponential function, the Laplace transform of an exponential function. So instead of a, I use instead of a on the one that we solve, so this time it just uses n. So it's just 1 over s minus n. And then if it is t raised to n, okay, so any variable raised to a constant, so n here is constant. That would be n factorial over s raised to n plus 1. So in short, we could use this table. We don't need to derive everything. So using the definition formula or using the definition of the Laplace transform, so we could right away use the following. So on number 4, so we just have the sine nt, so n all over s squared plus n squared. So if it is cosine, it's just an s. Okay, so sine and cosine would have the same denominator. So s squared plus n squared. If it is sine, the numerator is n. If it is cosine, the numerator is s. So same as true with a hyperbolic sine and hyperbolic cosine. So the only difference it's minus, okay, on the denominator. Then the numerator would be the same as the basic sine as well as the cosine. So those are the table that we have. So in finding the Laplace transformation. And next we have as well some theorem, but I guess we can just go back to those theorems so once we have the examples for that. Let's have our first example. Find the Laplace transform of f of t is equals to t squared. So using the definition of Laplace transformation. So this is very specific, although I already introduced the table. So the table will yield to a shorter solution. But on the example, so we have to find the Laplace transform using its definition. So we are to find the Laplace transform of t squared. And that is equivalent to the integral of e raised to negative st. And then our function is t squared. And then dt. So from 0 to infinity. So to find the integral of this, so we could use integration by parts. So we're in our u, so would be t squared, or the simpler one, so we could use the tabular method. So e raised to negative st, so t squared would be 2t, and then 2t would be 2, then we'll have 0. So this one, so the integral of e raised to negative st, so would be negative 1 over s e raised to negative st. Then we have a positive 1 over s squared e raised to negative st, and then a negative 1 over s cubed e raised to negative st. So for the tabular method, so this would be positive, a negative, and a positive. So the Laplace transform of t squared then, so would be, so I'm just going to use an f of s. So that would be negative t squared all over s e raised to negative st, and then a negative as well, 2t over s squared e raised to negative st. And lastly, we have negative 2 over s cubed e raised to negative st. Then we're going to evaluate it from 0 to infinity. So for our f of s then, for the first term, so we would just have e raised to negative infinity. So from here, so since each term involves an exponential function of e raised to negative st, so everything would be e raised to negative infinity would be 0. So the three terms, so 0 plus 0 plus 0, so that would just be 0. And then minus, when t is 0, so definitely our first term, so t squared, it's already 0. 2t is already 0. So what would remain there? So would just be negative 2 s cubed, and then e raised to 0, so would be 1. So that's giving us the f of s to be equivalent to 2 over s cubed. Okay, so 2 over s cubed. So that would be our f of s. So that's the Laplace transform. So t over s cubed. So let's have another example. So this time around, so find the Laplace transform using the definition of Laplace transformation of e raised to negative 3t. So the Laplace transform of e raised to negative 3t, so would be equal to the e raised to negative st, and then e raised to negative 3t dt, that is from 0 to infinity. So this would be equal to from 0 to infinity, so e raised to negative, we could have an s plus 3 there, negative s plus 3t, then dt. So therefore, the neutralizing factor is negative 1 all over s plus 3. Then we'll have e raised to negative s plus 3 times t, and that is from 0 to infinity. So negative 1 all over s plus 3 then, so we'll just have e raised to negative infinity is 0, then minus e raised to 0 would be 1. So therefore, giving us 1 all over s plus 3. So as our, or the Laplace transform of the given function, e raised to negative 3t. So next, let's have another one. So this time it's an hyperbolic. It's hyperbolic sine of 4t. So I guess this is a bit longer. The Laplace transform of hyperbolic sine of 40, so that is equal to the integral of e raised to negative st, and then the hyperbolic sine of 40, and that is from 0 to infinity dt. So in here, we could employ, integration by parts. Okay, so since it's a product of an exponential function and a hyperbolic sine function, so I could let u to be hyperbolic sine of 40, and then its derivative, so would be 4 cosine or hyperbolic cosine of 40, and then our dv would be negative 1 all over s e raised to negative, our dv so should be e raised to negative st dt, and then our v would be negative 1 all over s e raised to negative st. So that's forming the Laplace transform of e negative st hyperbolic sine of 40 dt, so to be equivalent to uv, so negative 1 over s e raised to negative st hyperbolic sine of 40. And then I'll have a negative v du, so a negative and a negative, so that would be plus. Okay, so plus 4 over s. Okay, so plus 4 over s, then the integral of e negative st hyperbolic cosine of 40 dt. And next, so we could have our u again, so u to be equivalent to, so let's say, a hyperbolic cosine of 40. So du then would be a 4 hyperbolic sine of 40 dt. Our dv is e raised to negative st dt, so our v then would be negative 1 over s e raised to negative st. And thus the integral of e raised to negative st hyperbolic sine of 40 dt, so is negative 1 over s e negative st hyperbolic sine of 40, and then uv. So our v is a negative 1 over s, so multiplied it with a negative 4 over s, so that would give us a plus 4 over s squared, and then e raised to negative st hyperbolic cosine of 40. Okay. And next, so negative uv minus v du. Okay, so suppose this is this, so this should be positive. So plus 4 over s, and then so therefore this would become negative. So negative 4 over s squared. And then finally, so we could have the negative v du. So negative v du, so that would make it a negative and a negative, so positive, so plus 4 over s times 4 over s, so I'll have a 16 all over s squared, and then the integral from 0 to infinity, so e raised to negative st hyperbolic cosine or hyperbolic sine, so hyperbolic sine 40 dt. And then from here, so we could combine, or we could transpose this one. Okay, so that would make it 1 minus 16 all over s squared. Then multiplied it with the integral of e raised to negative st hyperbolic sine of 40 dt. So to be equivalent to 1 over s e raised to negative st hyperbolic sine of 40 minus 4 over s squared e raised to negative st hyperbolic cosine of 40. And this one, so will become s squared minus 16 all over s squared, and then dividing it on both sides of the equation, so that will yield to the integral of 0 to infinity, so from negative e raised to negative st, so hyperbolic sine of 40 dt, so to be equivalent to s squared all over s squared minus 16. Then everything is multiplied with negative 1 all over s e raised to negative st, and then sine hyperbolic 40 minus 4 over s squared e raised to negative st hyperbolic cosine of 40. And then we're just going to evaluate it from 0 to infinity. So in here now, so we can find the integral, or we could evaluate this one. So our f of s then, so would be equal to s squared all over s squared minus 16. And then evaluating the infinity, so we would be e raised to negative infinity, so would be 0 and 0. So we'll just have 0 for the infinity. And then when t is 0, okay, so for t which is 0, so sine, hyperbolic sine of 0, so would be 0. So leaving us a 0 here, and then a minus, e raised to 0 is 1, then cosine 0, hyperbolic cosine of 0 is 1 as well. So leaving us negative 4 all over s squared. And thus leaving us to have s squared all over s squared minus 16, then multiplied it with a positive 4 over s squared. So s squared would cancel out, so our f of s then, so would be equal to 4 over s squared minus 16. And that would be, okay, so the Laplace transform of hyperbolic sine. Okay, so hyperbolic sine of 40. So hyperbolic sine of 40. So those are the longer method. Okay, that's the long method on how to do it. Let's have, okay, the simpler one. So the direct method. So for this, so we will be using some parts of the table for us to get the answer or the Laplace transform of the given function. So instead of doing it using the longer method, so we're just going to employ formulas on the table. So our f of t is equal to 4 plus 3 e raised to negative 2t. So the Laplace transform then, so would just be the Laplace transform of 4, and then plus, in Laplace transformation, so if we have a certain function, in this case an exponential function, and then it's just multiplied with a constant. So similar in integration, so we could just move out the constant and then just take the Laplace transform of the exponential function 2t. And then I'm just going to write those on the table, that the Laplace transform of a constant c, so that would just be equal to c over s. So while the Laplace transform of e raised to nt, okay, so that would just be 1 all over s minus n. And based from this, we'll be able to find right away so our answer. So that would be the Laplace transform of 4, so which is a constant, so that would be 4 over s. And then plus 3, so multiplied it with the Laplace transform of e raised to negative 2t here, so that would be 1 all over s. Then since it is a negative 2, so negative times negative 2, so that would be plus 2. So combining, so we could have s and s plus 2 as the LCD. Then we'll have a 4 multiplied it with s plus 2, then plus 3 times an s. So f of s then, so would be 4s plus 3s, so I'll have a 7s, then plus 4 times 2 is 8 all over s times s plus 2. So that would be the Laplace transform of the given, so 7s plus 8 all over s times s plus 2. So it's very direct. So as long as we know how or what would be the content of our Laplace transform table. Let's have another one. Find the Laplace transform of f of t is equals to cosine 5t plus sine 2t. So using Laplace transform table. So our f of t here is cosine 5t, then plus sine 2t. So our f of s then, so would just be the Laplace transform of cosine 5t, then plus the Laplace transform of sine 2t. So based from our table, so the Laplace transform of cosine nt, so that would be equal, so if it is cosine, the one on the numerator is s, and then all over s plus n. So that is for the cosine, s squared. And then the Laplace transform of sine nt, so would be n, then divide it with s squared plus n squared. So s squared plus n squared. So therefore, so the Laplace transform of cosine 5t, so would be s all over s squared, so plus our n is 5, so 5 squared would be 25. Then plus sine 2t, so n is 2, so 2 all over s squared plus 2 squared is 4. So and that, so we could combine, so f of s then, so would be s squared plus 25 multiply it with s squared plus 4, so s times s squared plus 4, then plus 2 times s squared plus 25. So f of s then, so we'll have s cubed, and then plus we'll have 2s squared, then plus 4s, then plus 50. And that would be divided with s squared plus 25 times s squared plus 4. So that is the Laplace transform of the given function f of t. Let's have another one. So our f of t this time, so it's equal to e raised to t minus e raised to negative t squared. So as you can see here, or based from our previous examples, so in this case, what separates our two functions, the cosine function and the sine function, is just an algebraic operator, which is the plus. So similarly, on example number 4, so a constant is separated with an exponential function by an operator which is an operation which is addition. So in those cases, so we could just take the Laplace transform of its given term. However, in example number 6, okay, so we have two exponential function e raised to t minus e raised to negative t. However, it has an exponent, so which is 2. So in this case, the similar on the principle in integration, so we could not just simply take the Laplace transform of e raised to t and then minus the Laplace transform of e raised to negative t, and then afterwards, so we're just going to get the square of the 2. So in here, so we have to make sure that the operations involved is just a plus and a minus. So from there, so we could right away find the Laplace transformation. But if there is any other operation, okay, so such as multiplication, such as division, or such that it is raised to an exponent, or we are finding the square root of the given function, so we could not do the Laplace transformation right away. So we have to perform the operation first. So in this case, it is squared, so we have to square it first. Okay, so before applying or before finding the Laplace transform. Although there are cases that if it is a product of two different functions, that would be possible if we're going to use some theorems, just what was mentioned before. So we have the shifting theorem or the multiplication by t raised to n. Pero other than that, so if we could perform the operation first, so perform the operation first before finding the Laplace transform. So in this case, so e raised to t and then square it, so that would give us e raised to 2t, and then minus 2 e raised to t times e raised to negative t, and then I'll have a plus e raised to negative 2t. So that would be our expansion here. However, so this one would be e raised to 2t, so I'll start with the other one, so plus e raised to negative 2t, and then e raised to t and e raised to negative t, so that is equivalent to 1, so that would just leave us with 2. So from here, so from a function, so which involves an exponent which is 2, okay, so this one, so we're able to transform it into a function so which only involves a plus and a minus. So therefore, we can now right away so find the Laplace transform of the given equation. So this is exponential function, so that would just be 1 all over s minus 2, and then plus 1 over, this would be s plus 2, and then minus 2 all over s. So f of s then, so would be s minus 2, then s plus 2 times s. So this would be s times s plus 2, then plus s times s minus 2, then minus 2 times s minus 2, and s plus 2. So combining, so we have s squared, or distributing it first, so s squared plus 2s plus s squared minus 2s, then minus, so this one is a sum and difference, so we could combine this as, so we can distribute right away, s squared, so negative 2s squared, and then a negative 4 times a negative 2, so a positive 8. Then just divide it with s, and s squared minus 4. Right, so s squared minus 4. And that's, so 2s minus s, and then we have an s squared plus s squared minus 2s squared, so that would cancel out as well. So leaving as the f of s, so to be equivalent to 8 all over s times s squared minus 4. And that would be our final answer. Let's have another example. For example, number 7. So we are to find the Laplace transform of 4 cosine squared 40 and then minus 2. So in this case, the two terms are separated by an algebraic operator, so which is the negative. So we have a constant 2, so in which we can find the Laplace transform. But for cosine squared 40, so we don't have a direct transformation for that. What we only have is just for cosine, but the cosine squared is a different thing. So in those cases, so we have to transform, or we have to use some identities, so for us to transform the cosine squared into a plain cosine. So remember, we have the identity, so cosine squared 2a, so minus 1 is actually equivalent, or 2 cosine squared a, so 2 cosine squared a with minus 1, so would be equal to cosine 2a. So since what we have here is a cosine squared, okay, so it would appear here that 2 cosine squared a, so if a is 40, so let's say a is 40, so therefore, so 2 cosine squared 40 then, so minus 1 would be equivalent to cosine 2 times 40, which is 80. So in here, so our f of t, so we could factor out 2 here, so making it a 2 cosine squared 40, so minus 1, so which resemble as this one, and that is equivalent to 2 times cosine 80. And thus, so we can now find the Laplace transform of this, so to be equivalent to 2, and then the Laplace transform of cosine 80, so would be s all over s squared plus 8 times 8, so 64. Or f of s would be 2s all over s squared plus 64. 2s over s squared plus 64. Next, let's have another one. So f of t is equals to 2t minus 1 raised to 3. So in here, we need to expand. So using binomial expansion, so we could use the Pascal triangle. So if we have a 1 here, so a 1 and a 1, a 1, 2 and a 1, a 1, 3, 3 and a 1. So that would give us, so f of t then, so would be equal to 1. Then multiplied it with 2t raised to 3. And then we have a negative 1, so raised to 0. And then plus a 3, so multiplied it with 2t squared. A negative 1 raised to 1. Then plus 3 times 2t, a negative 1 squared. Then plus a 1. Multiplied it with 2t raised to 0 and a negative 1 raised to 3. So f of t then, so would be negative 1 raised to 0 is 1. So we have 8t cubed. And then we'll have a negative of 4t squared. So 4 times 3. So we'll have 12t squared. Then a positive 60. And then a negative 1. So we have 8t cubed minus 12t squared plus 60 minus 1. And therefore, the Laplace transform then, so we have t squared, so that is 8, and then n factorial. So remember that t raised to n, so the Laplace transform of this, so would be equivalent to n factorial over s raised to n plus 1. Or that would be, so 3 factorial, so divide it with s raised to 3 plus 1, which is 4. And minus 12, 2 factorial, so divide it with s raised to 3, then plus 6, so 1 factorial all over s squared, and then minus 1 all over s. So f of s then, so would be 3 factorial is 6. 6 times 8. So we have 48 over s to the 4th. Then minus 24 s cubed plus 6 s squared minus 1 all over s. So we could combine. So LCD would be s to the 4th. So we'll have 48 minus 24s plus 6s squared minus s cubed. So 48 minus 24 okay, so 48 minus 24s plus 6s squared minus s cubed all over s to the 4th. So that would be our final answer.